Good morning, everyone. I am Professor Mohamad Kassem from Northumbria University. Thank you for your invitation. It's my pleasure to present here. In my presentation, I'll be proposing a solution to improve the productivity of equipment in earthwork projects using digital twin. Earthwork equipment pose significant challenge to construction projects, especially in large infrastructure projects. From empirical observation in HS2, we realized that equipment utilization rate can be as low as 30%. We also found there is a crossover and duplication that can go up to 5%, which is a significant waste. Also, in terms of emissions, CO2 and NOx emissions, there is a report by the London Greater Authority showing that up to 12% comes from construction equipment in and around London in terms of total emission. Equipment are really important in terms of their incidence on project budget. They can amount in certain projects up to 40% of the budget. They are always on the critical path. They are important from health and safety perspective. They cause traffic and environmental emission like we have seen in the previous slide. Their productivity, we can say that their productivity can affect the overall success of a construction project. And it is really important to measure their productivity in order to improve it. We looked at current processes of measurement of productivity, and current processes are really manual, are time and resource intensive, and they are error prone, and they are impractical in large projects. We, driven by this important gap within the industry, we formed a project team, including technology partners, research partners, and demonstration or process partner, I can call them. We have a build stream who is a startup tech company involving in developing IoT for tracing resources across the supply chain, BIM Academy in terms of BIM technologies, Northumbria in terms of machine learning and BIM, Walters, who are a large earthwork contractor with a significant fleet of equipment, and Costain and HS2 for demonstration site, and we as well had access to their project control team and site team. We were funded twice by the Transforming Construction deal. The first time it was a feasibility study, and you can see the project title here was a 1-year project, and then we had a larger funding for a longer time under the round 2 of the Transforming Construction deal, and this is the project title where we developed the full solution. I'll show you in the rest of my presentation, I'll show you the result from both projects, and I'll show you how we learned from the feasibility study some lessons that we went to address into the full project in phase 2. The first thing we did in our feasibility study project is to understand the use cases where digital innovation can help, and the current processes, how the current processes are performed. We interviewed a team from Costain who are involved in HS2 on in earthwork projects, and we identified 6 use cases that are clearly explained in this table with a description and a metric. In the rest of my presentation, I will focus on developing the solution for the first 3 use cases, which are all interrelated, are about estimating the volume of earth excavated. This is an important metric because clients pay earthwork contractor based on the volume of earth excavated, and contractor need to regularly report this metric. When we link this performance metric to the corresponding task and to the corresponding program, we'll be able to develop a project control solution, which is visual in this case because we are integrating BIM, machine learning, and IoT. Research in this area is not new really. It goes back to year 2000. However, what was lacking at that time is the automation using digital innovation, and the lack of live data from site, and the lack of experiments on actual site. You can see this result from this table here, and a full review in this paper on this link. There is lots of debate around the concept of digital twin. Whether what we are presenting is a digital twin or not, it's a debatable topic. I wouldn't delve into detail due to time. There is this paper that addresses this issue around digital twin and other concepts. In our research, digital twin is manifested through the combination of IoT, BIM, and data analytics or machine learning. To address the first use cases I mentioned earlier, this is the general architecture in UML language. You can see we are using data from telematic system. I'll talk a little bit more in details about telematic systems here because currently telematic systems, these are default system installed on Earthwork equipment. We had to use existing system because we tried to develop our own IoT by build streams that listen to the engine, but every time we connected it to the computer on board, it was rejected. This was part of the feasibility study. We're exploring different options to get the data. So we used the telematic system to see was an obvious choice because the system are there to see what we can do. And we took the data. You will see what data we took later on from the telematic system. We use machine learning, deep neural networks to calculate or predict the volume of excavated. We link that to the corresponding task to update the model. We visualize that into a 4D BIM model, which is basically 3D over time. And within that environment, we applied earned value analysis to show the performance of the program. And finally, we developed a dashboard where we can visualize the result. It's more like for project planner and project manager to control the overall, to see the overall project performance. So this is really the high-level architecture. This was a feasibility study. Remember, it's phase one. We were not concerned about the integration much, but we want to show that these units like telematics, machine learning, BIM, they can work in tandem, and we will be able to integrate them if we would go into phase two of more like actual development rather than feasibility study. This is the data you can download from a typical telematic system installed on board. We can't use all this data because some of this data is non-numeric, some of this data is doesn't help us in terms of convergence of our machine learning algorithms. Some was incomplete, so we ended up refining our data input, and we had the data here, the data you can see on the left of this table here. This is the data we used. We did lots of feature engineering work to identify the data needed. This is statistics around the data we used in terms of data sets. We used more than 700 samples of data distributed across over 21 days. You can see we tried to for example, account for different equipment weight. We have equipment with small equipment that weigh up to 13 tons and more larger equipment. And the reason we used as well 21 days as a minimum of data is to account for potential weather variation and soil variation and so on. And we implemented our using the data and input. We used Google Cloud Platform. We tested different gradient descent algorithm. Once we have identified our optimal one, we developed we optimized the architecture of our tool using this root mean square error to identify basically the smallest error and the best configuration. We identified this configuration where we had two hidden layers, one layer with 50 nodes and one layer with 25 nodes, and this is the feature, the data input that we had. And once we have identified our best architecture for the deep neural network algorithms, we went on to test it, and these are the results from the testing over 21 days. Here you have days, and here you have the volume of earth excavated and blue is prediction, and orange is actual. What you can see is we calculated the R square, which is a standard coefficient to judge the accuracy of prediction, and it was really good. It was 0.89, which is comparable with other research on similar problems. However, what we could see on some days, our error is larger than others. And looking at our data, we realized that this is because the site was a burial site with thousands of bodies covered there, and needed archaeologists to walk alongside equipment. So wherever we have days where the error is high, it's because you used to have mechanized walk alongside manual walk. So we were confident that the results are good. However, they are more valid or more applicable in an environment where in a more mechanized environment rather than a mixed environment, manual and equipment like we had here. At the end of our feasibility stage, we realized there is a good potential for automating and visualizing the productivity of equipment. However, there were also important challenges. The first challenge was our reliance on telematic systems by OEM providers. They don't provide data in a consistent way. They don't name things the same way. They don't define things in the same way. They have different data upload intervals. So they are really for automating productivity measurement. We need consistent data, and a fleet contain different OEM provider, and you don't have consistent data to address this problem. The other challenge was related to integration of live data feed for the BIM tools that are commercially available. We used Synchro in this project, and not only were not able to integrate live data feed, but also we're not able to develop the functionality we need for project control. Last but not least, we had issues as well, challenges for integrating the different components of the solution. We were lucky towards the end of the feasibility project, a new competition came by Innovate UK, phase 2 of the Transform and Construction deal, and we were awarded a project with bigger funding for longer period, in this case 18 months. And during that project, we aim to address this 3 limitation and develop the solution that overcomes these 3 limitations. And under the next phase, we had 3 objectives, which is to overcome the challenges we had in the first project. Is about developing our own bespoke IoT system rather than relying on telematic system. Develop data pipeline using Google Cloud Platform, and develop those around what we call whole round trip of each equipment, and we are using different type of data. You will see it later on, and finally develop our bespoke for these softwares. We went on to do that. Our partner Buildstream developed their own telematic, we could say telematics, their own mobile smart phone based application. Where we assign a unique ID to equipment, and there are 2 buttons, scan and go, basically on off. Driver need to press only 2 buttons, and we collect data from the IMU, accelerometer, the acceleration data in 3 direction, and rotation data in 3 direction, and location as well, so GPS coordinates. And we did at Northumbria our machine learning on this data using accelerometer data, gyroscope data, and noise data as well. And this is a methodology we adopted, but in this case we were concerned, we were not calculating the volume of earth excavated, we were calculating active inactive state in order to calculate the utilization ratio of each equipment. And this is the implementation of 3, we compared 3 machine learning algorithms that you can see here as ABC, and their detail is in this paper. And this is a sample of data, accelerometer data showing when the equipment is active and when it's inactive. And this are the noise data. This is the accuracy which we calculate comparing the prediction against the video data. So we captured as well video data as ground truth, and also to label the data for the machine learning algorithms. Interestingly here, this site is in Canada because we had winter here, the Earthwork season was closed, our researcher was based in Canada, so she went and found a site in Canada and found a site, and she installed her mobile phone on a excavator to collect the data needed. The results were really encouraging. We were able to, activity recognition, we were able to identify it with high accuracy. Of course, we have different models. They had slightly different results, but all results were really very promising. The highest was with DNN. Similarly, we did with utilization ratio, and the accuracy, comparing it to the actual one, we realized the best model was the DNN and required data input, all data input, accelerometer, gyroscope, linear acceleration, and noise level data. More detail are in this paper. Moving on to the next step in terms of machine learning, the activity we did was simple one, to recognize active, inactive equipment. But what we need to do really, we need to apply this across the whole round trip. You can see these 6 steps here, and the step apply to each equipment, to all equipment types. So we need more data about each of those steps for a mixed fleet equipment, and we should retest our approach and see if we can still get accurate data. In terms of front end, BIM Academy developed their application here, which we can manage all planning data, link equipment to programs, back end to manage all data, front end in 2D and 3D. So we can really, this application is currently commercialized. You can see it on BIM Academy website. In terms of limitation of future work, as I said earlier, the actual machine learning work was done on a demolition task in Canada. We are waiting data from full round trip from the UK to conduct more complex activity recognition techniques. We need to explore as well other, a mixed fleet, not only excavators. One problem we are still facing is how we can identify the link between equipment and program task, because when equipment move from one task to another within the program, and of course we need to investigate other use cases. Thank you for your attention.